Hey guys, today I wanted to go ahead and explain how molecular geometry can affect polarity. And we already know that polarity can affect your different types of IMF or intermolecular forces that can exist between molecules. So one major struggle that students have is just determining if something's polar or not, and especially if it's more than just a binary or an element or a molecule that has just two elements. So here you'll see all of these have more than two for the most part, and if you're having more than two, how do you determine its polarity? So what I did is I broke down all the different types that you've learned in terms of the molecular geometries and whether or not something is going to be polar or not. We're going to start with tetrahedral and we'll go all the way down. So for tetrahedral, I'm not sure if you guys remember, but tetrahedral will have one element surrounded by four. Tetrahedral normally is going to be nonpolar as long as the elements that surround the central atom are all the same. Think of it like even though fluorine is really polar, it's an even tug of war between all of the fluorines for carbon's electrons. So it's even, it's going to be considered nonpolar. It's an even sharing of electrons. And if you want to take it a step further, if it's nonpolar, then it's really just going to have a London dispersion IMF. Well, what happens if you have tetrahedral and it is polar, or what would that look like? You'll see for the second one, it is polar. The reason why the second one's polar and the first one was not, they're both tetrahedral, but the second one, the elements that surround carbon are not all the same. So you have fluorine and you have hydrogen, and if you listened to my Zoom or you attended the Zoom, you heard that fluorine and hydrogen, their electronegativities are really different. And so there's normally always an uneven sharing of electrons there that are present. Where carbon tetrafluoride, all the fluorine are surrounding carbon, they're all even. They all have high electronegativities, but it's all even. So it's considered nonpolar. But for this one, it's polar because you have two fluorine at the bottom and you have two hydrogen on the top, and they're not going to share carbon's electrons evenly. You're going to have more of a pull in terms of electronegativity on the fluorine, creating your partial negative charge. And if you're wondering like which one gets the partial negative and which one gets the partial positive, the one that has a higher electronegativity value, and you can find electronegativity chart online. You don't have to use necessarily the one you might have gotten from me in class. So you can just find any electronegativity chart on Google and you can use that. But you'll see that fluorine's a 4 and hydrogen's a 2.1 on that chart. And so fluorine, because it's high, is going to pull those electrons closer to it, creating the partial negative. So the one that has a higher value on that chart gets the partial negative. And the hydrogen, having a lower value, is going to get the partial positive. Anytime you have that partial negative and partial positive charge, you're going to have polarity. And because this is polar, and you can see that you have an H and you have an F, which is a part of the fun series, you'll actually have hydrogen bonding going on here. The next one we need to go over is trigonal, planar, and pyramidal. Trigonal planar, if you're just trying to figure out how do I know if it's planar, how do I know if it's pyramidal, you might have forgotten that. Trigonal planar is when you have one element surrounded by three, but there are no unshared pairs of electrons on the central atom. So here you'll see boron trihydride is our planar shape because boron does not have unshared pairs of electrons, allowing those bond angles to increase and for the hydrogens to kind of spread out. Normally, your planars are not going to be polar, and in this case, boron trihydride is not polar. Your leading IMF here would be a London dispersion, but if you look down, you have your B, F, and H2. So what would you do here? This is definitely going to be polar because now the three surrounding one are not the same, just like above here. So your F is going to be your partially negative charge, and your H's would be partially positive. This would definitely have polarity, so you definitely have dipole-dipole, but you'd actually have hydrogen bonding going on with this one as well, because you have your H's and you have your F, which would be a part of your fun series. So usually planar is not polar, as long as all of the elements surrounding the central atom are the same. If they're not the same, you need to figure out if the ones all surrounding the central atom are very similar, making it still fall in the nonpolar range. If it's not, where you can see H and F are really different in terms of their electronegativities, Again, F has a 4, H has a 2.1. So if they're really different from each other, it's going to be polar. And the one that has a higher electronegativity is going to give you that partial negative charge. And the one that, and this would be your partial negative charge, and this one would be your partial positive here. What about pyramidal? Pyramidal's really normally going to be polar, and here's why. So you can see here as just an example, you're going to have your nitrogen trihydride. Pyramidal, by definition for molecular geometry, is when you have one element surrounded by 3, and the element in the middle has unshared pairs of electrons, which are these guys right here. Those are going to help with the partially negative charge. So normally speaking, when you have a pyramidal shape, the one in the middle, so I'm talking about nitrogen, is going to be more electronegative than the ones on the outside, so these guys. And it's going to have unshared pairs of electrons, making it, normally speaking, going to be your partially negative charge, and then the ones on the outside are going to be your partially positive charge. Again, every case, every scenario is different, so you have to pay attention to what's present, but that's a good example of a pyramidal shape that is polar. And linear and bent. Linear is just normally going to be when you only have 2 elements, or when you have 3 and you have those double bonds. Typically linear is nonpolar, but not always the case. Linear can definitely be polar as well. So let's go over an example of each. If you have a, let's say carbon dioxide, that's a great example of a nonpolar molecule where you have those double bonds. You have an even sharing of the electrons of carbon from the 2 oxygen because they're both the same element. I had to add those unshared pairs that got cut off. But you'll see for this, if you have the same elements on either side of your central atom, it's going to be nonpolar. So it's like an even tug of war between the two because they're both the same element, so they have the same electronegativity. Because this is nonpolar for CO2, it would have London dispersion in terms of its leading IMF. What about a linear structure that just has 2? Well, it can go either way here. It's 50-50 chance. If you have 2 of the same element, it's typically nonpolar. An example of that would be difluoride. Try to draw those unshared pairs of electrons. This is going to be nonpolar. But if you have something like this, which is very common with 2 elements, and each element's different, normally speaking it's polar. The one that has a higher electronegativity based on that electronegativity chart will win in terms of which one gets that partial negative. The one that is smaller will get partial positive. And again, that's because those electrons that are being shared are getting pulled closer to fluorine because fluorine has higher electronegativity. By definition, electronegativity is just how much an atom is attracted or how much the electrons are attracted to a particular atom. So if fluorine has a higher electronegativity, H's electron is going to get pulled closer to F. Because HF again has an H and it has an F, not only is it going to have dipole-dipole, but it's actually going to have hydrogen bonding as well. So the leading IMF here would be hydrogen bonding. The only reason I'm pointing that out is because it is important to know that molecular geometry and polarity, the reason I'm teaching this is really to be able to determine the leading IMF that's present in a given molecule, and that's what you're going to be tested on. So, and that's why I keep saying that to you. Okay, what about bent? So linear and bent is normally when you have 3 atoms, having 2 surrounding that one. Bent is almost always polar. You can see here for water, you've already learned about water having hydrogen bonding. It has the O from the Fun series. Fun series again was your FON. And an H. If you have an H with one of these, you're going to have hydrogen bonding, normally speaking. And so here you have your H's and your O. Why is it that this bent structure is going to be considered polar? That's where a lot of students struggle. It's polar because your oxygen has a higher electronegativity than your hydrogen, and those unshared pairs of electrons make it even stronger of a force, of a leading IMF. So if you have like another water molecule that comes by, right? These are your partial positive. That attractive force, that IMF that we keep talking about, is going to occur between your H and your O here. And then if you had like another water molecule here, you're going to see that, let me go ahead and do positives just so you guys can see. It's your negative. Again, you're going to have another intermolecular force, hydrogen bonding occurring between this oxygen and that hydrogen being partial positive, this oxygen being partial negative. So those are your IMFs, but in terms of just determining if it's polar or not, oxygen has a much higher electronegativity than hydrogen. Hydrogen's your partial positive, oxygen's your partial negative because of that. So the one that's higher with electronegativity is going to take on your partial negative charge, and the one that's lower will take on the partial positive here. So bent, normally speaking, is always going to be polar. In terms of IMFs, really quick, just so you guys can hear that from me one more time. Weakest to strongest, I'll go in order. And I'll tie in your molecular geometry just so this hopefully will help you. If you have a non-polar molecule, based on what I showed you above, the leading IMF will be London dispersion. London dispersion is the weakest IMF, but that's the only IMF that can occur for a non-polar molecule. If you have a polar molecule without hydrogen and without your fun series, so no H and no FO or N, it's going to be considered dipole, and think of it like the second one down. It's a little bit stronger than London, but not as strong as hydrogen. Then you can have a polar molecule that has your F, O, or N, so your fun series with a hydrogen. You don't have to have F, O, and N together with H. You just have to have one, so fluorine, oxygen, or nitrogen with H for it to be considered hydrogen bonding. And that is considered the strongest of all of your van der Waals forces. So just make sure that you kind of understand what's the strongest, what would be the leading IMF. The other thing I discussed in the Zoom session is that if you have hydrogen bonding going on, you actually have dipole and London dispersion going on, but the one that dictates your melting points, your boiling points, and just a lot of the behavior is going to be your strongest or leading IMF. So here again, it would be your hydrogen, then dipole, and then your weakest would be London dispersion. I hope everyone is doing well. I miss seeing everyone in class. And again, if you have any questions about this content, please feel free to email me. Bye.